This is the 2005 free response questions 4 through 6, and in questions 4 through 6, this is the no calculator section, so you should not be using your calculator to work on any of these questions. As you can see from the annotations that I've already provided to you in our Google Classroom, this is a traditional problem, and it is totally an all about me sheet problem. I haven't seen too many of these in the most recent free response questions, but that doesn't mean that this year that they won't do that. An all about me sheet problem is a problem that you want to get all the points on because it's not that hard. And if you notice, they've given us all the information about an original function, the first derivative, and the second derivative in a table. So my strong recommendation to you is to transfer this information out of the table and on to number lines. Now I know that can take a little bit of time, but I think it's time that's well spent so that you can interpret the number lines more easily than you can look at the information in the table. We have f original, which is a function, and that function is continuous over the interval from 0 to 4. The function f is twice differentiable, meaning that f has a first and a second derivative except at x equal to 2. And we can see that in the table right here that there is no first derivative nor is there a second derivative at x equal to 2. The function f original and its derivatives have the properties indicated in the table above, where d and e indicates that the derivative of f do not exist at x equal to 2. Letter A. For 0 to 4, find all values of x for which f has a relative extremum. Now, extremum means either a local max or a local min. Determine whether f has a relative maximum or a relative minimum and justify your answer. Do not forget to justify your answer. So I'm going to believe that you transferred the information onto a number line, and let's take a look at the scoring guide for correct answers. So in letter F, f has a relative maximum at x equal to 2 because f prime changes from positive to negative at x equal to 2. In your answer, I would also like you to say that f prime of 2 equals 0. That establishes your critical number. So in letter A, you get 1 point for identifying x equal to 2 as either a local or max or min, and you get 1 point for the correct identification of relative maximum with your justification. In letter B, on the axis provided, sketch the graph of a function that has all of the characteristics of f. So this is where your number line would be really, really, really important. You're going to go really slowly, and when you sketch that graph, you're going to begin with the f row. So at 0, you're going to have a point at -1. At 1, you're going to have a point at 0. At 2, you're going to have a point at 2, 2. And at 3, you're going to have a y value of 0. So you're going to put those points on your graph first, and you can see those points here. So there's a point. There's a point. I think it was 2, 2. There's a point, and I would want you to make those points very evident, and then 3, 0. So that's how your graph would begin. And then you're going to read your number line to see that in this region from 0 to 1, the graph of f increases because the first derivative is positive, but concave down because the second derivative is negative. Then from your second derivative number line, you'll notice that the concavity changes at 1. So you're going to switch from concave down to concave up. And remember, we talked about that sort of like creates sort of like a cubic function, and if you look in that little region, it looks very cubic. Concave up, can't draw my up arrow. Concave up and continuing to increase, so the first derivative is positive. Now remember that they told us in the chart, in the table, that the first derivative is not defined at x equal to 2, but f is continuous, so that means there can't be a vertical asymptote there, so there has to be a sharp turn. And then the first derivative is negative in the next region, and the second derivative is also negative, so we need to decrease and be concave down. The second derivative changes to positive after 3, so the graph is concave up. and the first derivative in that region is still negative, so the graph continues to decrease. So the main thing is you just need to go slowly and just use your eraser when needed. So let's see where the points come from. In letter B, we get 1 point for putting all the correct x and y values from the table and the behavior at 2, 2. In other words, your graph must be continuous at 2, 2 to get that first point. Second point, appropriate increasing, decreasing, and concavity behaviors. So if you messed up any concavity anywhere in the entire graph, you're going to lose that second point. All right, going on to letter C. In letter C, we have a new function g, and g is a definite integral. And f, we know from the FTC part 2 that f of x is the first derivative of g. So we've talked about many times the importance of establishing in your writing somewhere that g prime of x equal f of x. That's called a connection point. It's something that we look for very often in these kinds of questions. For 0 to 4, find all values of x where g has a relative extrema. So in order to figure out where the critical numbers occur, we're going to need to set g prime of x. Let's just go back up here. We're going to need to set g prime of x, which is f of x, equal to 0. So we need to figure out where f of x is equal to 0, and then we need to figure out where f of x changes signs. Important to remember, justify your answer. All right, let's look at the scoring guide so you can compare your answers to this. Got to turn the page. An important fact, study and know the All About Me sheet. 40% of your test, or at least a traditional test, is connected to these concepts. All right, so looking at the answers for letter C, to find a relative extrema, you first need critical numbers. So you need the first derivative of g. I just talked about that already in the video. So there's that connection point that I was talking about. We need to show the reader that we understand the connection between g and f, and there's 1 point for the connection, seeing that the reader has to see it written. 1 point for identifying the proper and correct critical numbers of 1 and 3, and 1 point for giving an answer with a justification. G has a relative minimum at x equal to 1 because g prime changes from negative to positive. And again, I want you to say g prime of, we already said that back up here, never mind. And then there is a relative or local maximum at x equal to 3 because g prime changes from positive to negative. And then finally letter D. In letter D for the function g, so we're still talking about our function g that was defined as a definite integral from part C. Find all the values from 0 to 4 at which the graph of g has a point of inflection. So now, to get point of inflection, we're going to go to g prime, double prime, which is f prime of x. Now remember, in our chart, or in our table, or in our number line, actually, we have the information that we need. The second derivative of g is the first derivative of f, so we're looking for where the first derivative of f changes signs. So we're going to see the answer D. The graph of g has point of inflection at x equal to 2 because the second derivative of g is the first derivative of f, changes sign at x equal to 2. Now notice let's pay attention to the note down here. To find points of inflection, you first need possible points of inflection. Thus, you need the second derivative of g. You can see from the table where f prime of x equals 0 or undefined, don't forget about that, to identify the possible points of inflection and whether there's a sign change at those values. 1 point for identifying x equal to 2 and 1 point for the correct justification. Question number 5. This is our particle motion problem. We have a car traveling on a straight road for the interval from 0 to 24 inclusive seconds. The car's velocity, so we have a graph of velocity. in meters per second is modeled by the piecewise linear function defined by the graph above. In my case, it's defined by this graph right here. So this is a velocity function. In letter A, find 0 to 24 of v of t. So we're going to accumulate area from 0 to 4 using geometry. Using correct units, explain the meaning. So we are interpreting a definite integral. So first, to accumulate area from 0 to 24, this is clearly a trapezoid right over here. So we're finding all of the area. Whoops, let's clean that up a little bit. So we're finding all of the area in this region right here, which is a trapezoid. So we're going to go from 0 to 24, and this is the, I think, looks like they did a triangle and a rectangle and another triangle, which is perfectly fine. It doesn't matter how you break the geometric region up, but you get 1 point for the value, which is 360, so be careful with your arithmetic. You do not have to simplify. You could have just set that up and been done with it. And then the meaning, we're going to say, in this case, all of the area is positive. You could say something like, the distance, the definite integral represents the distance the car travels from 0 to 24 seconds measured in meters. Or it could be, you could say change in position, you could say displacement, because in this case all of the area is positive and the displacement and the distance equal to each other. If you have a question about your particular write-up, please ask me when we have a question and answer session. Okay, you can read the annotations on your own. In part B, find v prime of 4 and v prime of 20. So let's look at our graph over here. Remember, this is the graph of v, and we're trying to find v prime, the first derivative of v at 4, and the first derivative of v at 20. Well, notice that we have a sharp turn right here at t equal to 4. So there is no v prime. The derivative of v prime is not defined because the left derivative does not equal to the right derivative. Now you're going to have to justify that, and you're going to have to be clear. So the biggest part of this question is about, do you understand how to justify differentiability? If you have not taken some time to study and pay attention to differentiability, now would be the time to make sure you know how to write that up. V prime of 20, notice that t equal 20 is sitting on a line segment, so the derivative would be the slope. In this case, it's going to be a fall of, how much is that? A fall of 20, so down 20, and to the right, 8. And so 20 over 8 would be the slope or the derivative at 20. Let's look at the scoring guide. So we're going to say v prime of 4 does not exist because, and this is how we write up our justification, the left derivative, so this is the slope on the left, does not equal to the slope on the right, and your explanation has to be correct to get that first point. The second point is for getting the correct number for v prime of 20, and it does not have to be simplified. You could write it just like that, or you can simplify it, or you can have a fraction that is not reduced. And they did ask us for units, and it has to be meters per second squared. All right, let's take a look at letter C, which I think is, well, let's talk about the student work right here. Student number 1 work who received full credit, they did not, I don't know that in this particular, remember this is 2005, so things have moved forward. I don't know that this would be an acceptable answer at this point. They're saying that the left derivative does not equal to the right derivative, but they got full credit in 2005. That's all I can say about that. I don't want you to write your work up that way. Notice student number 2 did the what a lot of students do, oh, I see a sharp turn, and a sharp turn is not going to get any credit. All right, let's take a look at part C. In this part, we're asked to find the acceleration. We're writing the equation of acceleration, which is the derivative of velocity. So we know that acceleration is the derivative or slope of velocity. So since we have a piecewise linear, if you'll come over here and look at the graph, we have a line segment, we have a line segment, and we have a line segment. So we're literally finding the slopes of 3 line segments, but it's going to be a piecewise function. And they're telling us that it's a piecewise function from 0 to 24. So if you look at the answer, the slope of region number 1, this region right here, is a slope of 5 when we rise 20 and run 4, and that's on the interval from 0 to 4. If you had an equal mark here, I think you're going to be perfectly fine. The slope of the next segment, which is horizontal right up here, is a slope of 0. And if you put the equal to, we can talk about equal to's when we have our question and answer session, but for 4, you can put an equal at one of the 2 places, but not both places. Actually, wait a minute. Can you put an equal to at 4 acceleration? No, you cannot put an equal to there. Because the acceleration, there's no derivative at those sharp turns, so you cannot put an equal to here, but you can have an equal to here and here on the endpoints. That would be the only places where you could have the equals. And then in the third line segment, which is over here, we're doing a slope that we found on the other side, and so there's your piecewise function. So 1 point for finding the values, the 3 slopes, and you have to have all 3 of them correct, and 1 point identifies the constraints with the correct intervals. You don't have to state that a of t does not exist at t equal to 4 by not putting an equal to here and not putting an equal to here and here and here. You're not locking those in to have an acceleration at those points. So if you put the equal to's, you're not getting the second point. And then finally, for letter D, let's come back up and look at the question. Find the average rate of change. So that's easy. We're just going to do some slope from 8 to 20. So let me clear my graph here. And so we're going from 8, which is here, to 20, which is here. Oh, no, 20 is not there. That is incorrect. Sorry. It's from 8 to 20. So we're going to take these 2 points. Now to find the, we can see the y value of 8 is going to be 20. So we have the point 8, 20. And we have the point 20, I don't know yet. So we've seen this occur in some of our geometric problems before. In order to find that y value at 20, some students are going to guess and guess correctly, and I'm sure people are going to guess that the y value at 20 is 10. But to verify that, you really should be coming over here to do y equal, or y minus y1 equals m times x minus x1, and writing the equation of that line and substituting 20 to get the y value. After we do that, after we find that average rate of change, they want us to say whether or not the mean value theorem can guarantee a value where the instant rate equals to the average rate. Now, you're very familiar with the conditions of the mean value theorem. Conditions are very important. And we know that from 8, if we draw that secant line, I'm not going to try to draw it, from 8 to 20, in that interval, there's a place where there's no derivative. That means that on the open interval from 8 to 20, v is not differentiable, which therefore does not meet the conditions of the mean value theorem. So we're going to say no to that question. So let's come down here and look at the scoring guide. In letter D, the average rate of change is -5/6. Now, you may not leave your answer with V of and V of. You can leave it with those numbers like there. We know that that was, we know that the value of V of 8, V of 8 is a 0. I didn't calculate the V of 20, but you can figure that out. You get 1 point for the average rate of change, and then for explaining that the mean value theorem conditions are not met, you get 1 point. Make sure you know the conditions of every theorem because they will be assessed. And finally, question number 6. We see straight up we're going to be doing a slope field. We have a differential equation right here given. It's a slope generator. Letter A. On the axis provided, sketch a slope field for the given differential equation at the 12 points. Be very, very careful when you're creating a slope field, because if you mess up just one slope, you may be losing points. So you're going to substitute each x and y value into the slope generator, and your slope field should look like what you see in letter A. You get 1 point for the 0 slopes, meaning here and here and here and here you had to have a slope of 0. And you get 1 point for all of the other non-zero slopes. So that means that these slopes right here had to be negative, these had to be positive, these had to be negative, and these had to be positive. All of them had to be correct in order to get the non-zero slopes. Now, remember, we don't measure the slopes. It's mostly about the direction, the increase, the decrease, and they're headed in the right direction. In letter B, let y equal f of x be the particular solution. Now, they're not asking us to solve yet, to the differential equation with initial condition 1, 1. So when x is equal to 1, y is equal to -1. Write the equation for the line tangent to the graph of f at 1, -1, and use it to approximate f of 1.1. So we're going to begin with the equation of a line. Y minus y1 is equal to m times x minus x1. And in the prompt, dy dx is our slope generator. That's where we're going to get our slope from. So to find the slope of the tangent line, we're going to substitute 1, -1 into the slope generator, and we get a slope of 2. We substitute our x and y value, and we get y by itself. So we get 1 point for the equation of the tangent line. And then we're going to substitute 1.1. Now, this is a no calculator part. So when you do that, here's what I would expect to see as y. Y equal to, and we're substituting 1.1, 2 times 1.1 minus 1 minus 1. That would be the perfectly final answer for the approximation, and you'll get that 1 point. And finally, for letter C, we are finding the particular solution. So now we're going to separate, integrate, solve, solve. Separate, integrate, solve, solve. Define f of x with the initial condition of 1, -1. So there's where I'm going to find my plus c. So we're going to get 1 point for separating the variables. So we have a good separation. Multiply both sides by y. Multiply or move the dx to the other side. We're going to anti-differentiate. We get 1 point for both correct antiderivatives. So we got to get y squared over 2, and we got to get -x squared on the right. 1 point for the plus c. 1 point for substituting the x and the y value, and the c value turns out to be either 1.5 or 3/2. We're going to substitute the 3/2 back into place of c. And let me see, I'm going to show you an ugly version of this to show you how you could leave your answer. Give me 1 second here. So let me get my equation editor out and set this up for you. So I took my equation editor and I gave a little bit uglier version of the differential equation. So remember we had solved for c is 3 over 2, and I'm substituting it back in here. All right, now take a look at my work at this step. So this is me substituting the 3 over 2 back in place of c, and so obviously I'm going to multiply both sides by 2, but I didn't distribute it. I mean, I know it's not that hard to distribute it, but you don't have to, is the point that I'm making. And then to undo the square, I'm going to square root both sides. Notice again, I'm still not distributing. I'm just leaving the answer unclean so I don't make any silly mistakes. Now the biggest thing is to pay attention to the initial condition, because when you take that square root, you have to give the you have to look at the solution, and the solution y value is negative. So this is demanding and calling for the negative square part of the square root, not the positive. So this has to be negative to get that last point. And so that's the solution to the differential equation.